Thanks. So I'm going to talk today about the seismic signals that were generated by the 2014 landslide near Oso. So you've already heard a lot of the details of the event in the previous talks, but I'll just give a quick overview in case you just came in. So the source area is at the upper left here, and this was a slope that was about 180 meters high and had a slope angle of about 20 degrees on average. So from that source area, the debris avalanche flow flowed towards the southeast, and then it turned a little bit towards the south on average, but it really spread out over the entire plain, and that's where it inundated the neighborhood and crossed the highway and killed 43 people. And as Dick mentioned earlier, there was a landslide in 2006, often called the Hazel landslide, that happened in the same area, except it was a different style. It was more like a bunch of coherent material slumping down rather than this debris avalanche flow type event. So this was a very energetic event. We know it happened fast, and it generated very strong seismic signals that were observable as far as 450 kilometers away. But we have a pretty dense permanent seismic network in the area of the landslide. The closest station is actually this one right here called JCW. It's only 11.5 kilometers from the landslide, but this is just a short period station, so it can only record the higher frequency shaking, such as 1 hertz and higher. But there are a lot of broadband instruments in the area that can record all bands of shaking, or not all, but a much broader range of shaking. And so the two closest broadbands are located here and here relative to the Oso landslide. So first let's look at the data as recorded at JCW to get an idea of how the event unfolded. So this is a web recorder plot that shows 30 minutes of seismic data on each line. And so here is where the event starts, and it starts with the biggest signal. You see this very strong high-frequency signal that lasts about 2.5 minutes, and then there's a pause with a small little signal here, probably a smaller landslide in between, and then you have a second big signal that has about half the high-frequency energy as the first and a slightly shorter duration, but is still pretty significant. And then in the hours after the slide, you can see there's a lot of pulses still showing up, and these are most likely from pieces breaking off from the headscarp that has been left very unstable by the main event. So let's zoom in on the main part of the sequence, and this is what it looks like as recorded on a range of stations getting further away from the station, and you can see that the high frequency shaking attenuates very rapidly with distance. However, if we look at the signal at the closest broadband station, we can see that there's actually more to the signal than initially meets the eye. So the top line here is just the high frequency part that we've already seen, but actually within the same signal there are long period pulses, which are shown below here. And you can see that they're much stronger during the first pulse of high frequency energy than the second. You in fact can't even see them above the noise level during the second event. However, if we look at the next closest broadband station, we see the main event, but you can also see a little bit of a pulse from the second event that is barely above the noise level. So in fact, those two bands of energy are very distinct. They have two separate peaks. So here I'm showing a displacement spectrum of that first signal. The tallest peak is actually a noise signal, so I'm showing the background noise level in red here, and the landslide signal in blue. And so this tall peak is the microseism, which is generally from wave motion like ocean waves. So we can't see anything about the landslide in that band, but actually it looks like the peaks are two distinct peaks on either side of it. So we have these short period signals and these long period signals. So the short periods are thought to be generated by more stochastic processes such as disrupted flow, individual impacts of blocks, and also frictional processes, whereas the long period part of the signal is a more deterministic signal, and we have a fairly decent understanding of the source, the equivalent source mechanism of this part of the signal, which is a single force exerted on the Earth. And that force is actually opposite in direction to the acceleration of the landslide mass. And it's equal to the mass of the landslide times its acceleration. So force equals mass times acceleration from physics class. So when we have a landslide accelerating down a slope, it has a mass of m and an acceleration of a. And so the Earth feels a force in the upslope direction equal to m times a. And when the block is decelerating, the Earth feels a force in the same direction as the block because the landslide is accelerating upslope. So this theory dates back a couple of decades, kind of starting really with Canamori and Given, who looked at the 1980 landslide related to the eruption of Mount St. Helens. But a lot of people have used this since. And today we're going to use it to invert the long period signals to obtain the time series of forces that the Earth felt because of this event. So this is a pretty small event relative to what other people have done this for before. So the data is very noisy. So for a big event, you actually only need a few stations to obtain the force history. However, with this event, because the data is noisy, we used 18 stations and 20 channels, so mostly vertical channels, but a few horizontal. And that's to compensate for the low signal to noise ratio. So here's a map of all the stations we used. And at right is showing the actual data in its process form, and you can see the main event here pretty clearly, but it is hard to tell where the noise stops and the signal begins sometimes. And you can also see a faint pulse further out, and that is from that second event. So I will spare you the details of the inversion, but when we do it, we're able to fit the data pretty well with a 74% variance reduction where 100% is a perfect fit. So that's, the fit is shown in red here. And this is what the result looks like, and you had a preview of this earlier. So this plot here is showing the vector of forces exerted on the Earth by the landslide over time. It's showing all three components where blue is up, north is red, and east is green. And the shading around the lines indicates the uncertainty due to the noise, and we compute that by using the jackknife technique where we systematically throw away half the data and recompute the inversion. So this plot at right here is a LiDAR image of the landslide, and you can see I plotted 4 vectors here, and these are the peak horizontal vectors for each of these 4 time intervals. And I've plotted them at the same point because this, at long periods, we assume a stationary point force because the long period waves are not sensitive to changes in location. So that's why they're plotted at the same point, but I wanted to show relative to how the landslide flowed so you can see how the vectors compare to that. And then at bottom here, I'm showing the high frequency signal that you've seen many times already, but I've adjusted it for backwards for the travel time so it roughly lines up with the forces. So basically this is a vector that is being exerted on the Earth that's changing direction over time. So in order to better visualize that, I've animated it, and this will play through a couple times while I talk about it. So basically what we have here is what seems to be 2 cycles of acceleration and deceleration. We have a pretty weak pulse first that's lasts a little longer, that is consistent with an acceleration because it points upslope. Then we have a vector that points downslope consistent with a deceleration, but that's interrupted by the strongest force, which points upslope again, interval 3. And then after that, another deceleration vector. And then you'll see later, during this second high-frequency pulse, there is a part of this noise where the width of the uncertainties narrows significantly, and you can see there's a little upward pulse and a downward pulse. And so that is the very much weaker part of the forces associated with the second event. So you can see that is actually towards the front of the high-frequency signal, and it's normal for the forces to be earlier on because it takes time for the more chaotic processes to develop in the event. But this is not normal to have 50 seconds of activity before the high frequency. So at first we actually thought that this was an artifact or something because of the noise, because this first pulse is very weak. It's not very robust, but the second pulse, no matter what I tried, we couldn't get rid of it, so we were thinking more and more that it was real, but really the thing that made us think it was real was the eyewitness report that you heard about earlier, and I'll quickly summarize that again here. The eyewitness was standing on the edge of the slide. He could see across the floodplain to the river. He could not see the source area. And so he heard a really loud grating noise. Maybe he thought it was a low-flying plane. And they stood here trying to see if they could see what it was, but they could not see anything. And then that sound diminished. They dismissed its significance, turned around to go back to their house, and they estimate tens of seconds had passed by this point. But then a louder noise developed. They turned back towards the slope and saw the river thrown into the air and a high mass of earth pass in front of them at about 100 miles per hour. So this, in combination with the seismic data, does suggest that it could have been a two-part initiation sequence, where these first two pair of pulses are from slower coherent acceleration of part of the slope, maybe similar in style to the 2006 Hazel slide. And in fact, that slide did not generate any seismic waves that were observable at the closest station either. So it is possible to not have high frequencies from a pretty large event like that. And then we think the second pair of signals was related to the debris avalanche flow that inundated the valley floor. But that leaves the question of this last event here, and this has caused us a lot of strife trying to figure out what this is, but I think we actually have a fairly decent handle on it. So what we think it is actually this relatively small debris fall deposit up here that is on top of the landslide, the main landslide deposits. And it's initially we thought it was actually the slump block that's sitting up top there, because it kind of looks like a separate piece that might have come down later, but the geology doesn't indicate that it was collisional. So, and also the seismic inversion indicates that it probably was not that either, because the magnitudes of the forces are 5 times smaller for the second event, and you can have smaller amplitude forces for a similar mass, except for the fact that the time of it would be stretched out more because it would take longer to move. But this, in fact, has a shorter time scale than this one does, which suggests a more rapid movement of a smaller amount of mass. And if we zoom in on it, you can see that the vertical force here is actually just as strong as the horizontal parts of the force, whereas for the previous signal, the verticals are very much smaller than the horizontal parts. So this suggests that it was more of a vertical collapse that did still have some horizontal component to it. And that would be highly disrupted, which would generate a lot of high-frequency energy. So it has about half the energy of the first one. But the best way to illustrate this, how the style of landsliding really matters, is to show this video taken by the Snohomish County Engineering Services. This was taken about a month after the slide while they were monitoring the slope. So let me start it here.
Debris topple, there it goes.
And you'll see one piece break off first and kind of slide along the slope. And then in a second, they're going to go back and see a second piece
big one.
breaking off.
Wow.
And you see this is more of a topple, and it actually has some free fall component to it, and it has much more of a vertical impact. So this was actually recorded by one of the seismometers that the USGS installed right at the slide, and it was also recorded by that station JCW, which is 11.5 kilometers away. And you can see right at the slide, you can see those two pulses. The second one is much stronger because it had that very strong impulse, but by the time you get to 11 kilometers away, this first signal doesn't even show up at all, and you can only really see kind of a diffuse pulse related to the second event. So it shows that style really matters in how it's how it shows up in the seismic records. And then if we compare that event from the video down here with the signal from the main event, the biggest high-frequency signal, and that second big high-frequency signal, you can see if the scale is normalized, they look fairly similar. The main event has a longer duration, and these two events actually have fairly similar durations. But if you plot them on the same scale, we see that the energy contained in these high frequencies is only about 60 times higher in the main event than that tiny event. And we know that that tiny event was much less than 1/60th of the volume of the main event, whereas that debris fall deposit could conceivably be about 30 times larger than that event that we saw in the video. So it just shows that the style of landsliding really makes a big difference to how it shows up. And so I mentioned earlier that there were a lot of events happening afterwards. I call them aftershocks, though they technically aren't, but they're just smaller landslides coming off of the headscarp that's been left very unstable by this main event. So this plot here is showing the relative energy of the main event and that second event compared to all of the aftershocks happening in the 24 hours after the landslide occurred. And you can see there's a lot of events, 49 total. This is where the energy of that event that I showed the video of plots compared to these. But you'll notice that there's a lot of events clustered immediately after the landslide happened, and then it kind of dies off afterwards. And this is kind of interesting, at least to seismologists or like me, because it actually follows Amores' law for earthquake aftershocks. So this is showing the number of events per hour and how it decays over time, and it actually fits fairly well. So that's kind of an interesting aside. So in conclusion, we think that the initiation sequence for this landslide was actually fairly complex, and it possibly started with coherent slower motion tens of seconds before transitioning to the debris avalanche flow. And I also showed that the second high-frequency signal that was a few minutes later was actually most likely that much smaller debris fall that's up in the source area. And that's why actually none of the eyewitnesses mentioned anything about an event 4 minutes later, so that makes a lot of sense because it was way up there. And then also there were a lot of continued smaller collapses from the headscarp for weeks, and in fact they're probably still continuing but diminishing. And they kind of behave like aftershocks, at least on the short term. So that's it.
Great, we have a few minutes for questions.
Yes?
It's been stated that those that can't model are doomed to reality. It seems to me more plausible that the headscarp crack is like an earthquake. And we know from laboratory experiments that the maximum shears occur during the highest acceleration. So it seems likely that the initial crack created cyclic shear, which could have caused actual true liquefaction. And we had existing slide plane at residual stress. We know in lateral spreads the thin film of water forms on the permeability barrier, which in this case could have been the previous slide plane. And it's quite common for the existing slides to tow out in the river, which would explain the river being thrown up into the air. So I think you can explain it from more fundamental observation.
But how is that reflected in the seismic signals exactly? I don't quite understand what you're asking.
The first signal was caused by a big crack at the headscarp.
But the signal that we see here is very much a landslide signal. It has an emergent onset, so you can't see exactly where it starts. It peaks towards the middle, and it dies out gradually. That's what landslides look like in seismic records, at least in the high-frequency band, typically. Whereas an earthquake, you have very sudden first P-wave arrivals, and then you can see a second S-wave phase. And also earthquakes, we picked those up on the seismic stations as well, and there was not an earthquake associated with the beginning of this landslide.
So an earthquake is a propagation of a crack and a slip, which happened with the headscarp. Doesn't look like the headscarp actually crashed into the lower existing.
Okay.
That's my story.
Okay. Fair enough.
Any other questions?
You showed your force vectors pointing up a slope.
Mm-hmm.
Presumably this is just a force deviation from the normal way. So the actual force on the slope would always be down slope.
That's actually, that's not what people have found in the data. It goes back, a couple of decades, and at the very longest periods, the seismic signals generated by landslides are very consistent with an upslope force. So that's what the data show. And it's much more complicated in reality, but at the longest periods, it can be simplified in that way. So that's why it's called an equivalent force mechanism.
Very hard to believe.
Well, I can send you a lot of papers on it if you want. It's not theory that I've invented. It's pretty old.